Good morning, everyone. Today I'm going to present an analysis based on the paper by Faulin et al. Titled Distribution Companies Use the Analytical Hierarchy Process for Environmental Assessment of Transportation Routes Crossing the Pyrenees. The core of this work is the application of an AHP model to select the most sustainable freight routes. This methodology has already been adopted by regional leaders like Hydro-Enaza and Gamesa Eolica to internalize environmental costs. Let's look at the context of green corridors. We are witnessing a paradigm shift. Traditional logistics focused purely on economic KPIs like transit time and cost. However, we must now account for negative externalities, carbon emissions, acoustic pollution, and infrastructure wear. Driven by the EU Eurovignette legislation, the objective is to develop green corridors, roads designed to absorb freight flow with minimal ecological disruption. The conflict is centered in Pamplona, a strategic gateway for Iberian goods. The high reliance on road transport creates a bottleneck where two goals clash. Logistic providers want fuel efficiency and lower tolls, while local authorities demand urban safety and ecosystem protection. Our research question is how can we select routes based on holistic environmental impact rather than just cost? To resolve these conflicting goals, we use multi-criteria decision analysis. This allows us to rationalize trade-offs instead of seeking a single indicator optimum. The chosen tool is a Satier's analytic hierarchy process, which decomposes a structured problem into a multi-level hierarchy, from the macroscopic goal to specific criteria and alternatives. The objective is to translate expert judgments into transparent mathematical weight for strategic decision making. The execution follows four systematic phases: first, hierarchical decomposition to map the relationship; second, pairwise comparison using the 1 to 9 semantic scale to build reciprocal matrices; third, calculating the priority vector to compute criteria weights; finally, consistency verification. The matrix is only valid if the consistency ratio is less than 0.10, otherwise the judgment must be revised. In this specific model, the hierarchy is structured into four levels. At level 1, we see the macro criteria weights. The economic criteria account for only 20%, while social and natural areas are weighted at 40% each. This signals that ecological preservation is considered twice as important as economic cost. At level 2, 13 subcriteria are measured via GIF buffer zone to evaluate the five physical road alternatives A through E. Looking at the operational core, Road E dominates the economic matrix with a preference of 0.40 as it crosses low-value agricultural land. In the social matrix, Road A is preferred at 0.30 because it avoids urban center, while Road C and D are penalized for their proximity to population center. These matrices use square reciprocal use to ensure mathematical consistency. For natural areas, roads B and C score very low because they cross dense protected zones. When we calculate the final global results using the impact function, road E emerges as the optimal solution with a score of 0.297. It represents the best balance between peak economic suitability and high performance in both social and environmental categories. To validate these judgments, we check the consistency ratios. All values, 0 for economic, 0.006 for social, and 0.004 for natural, are well below the 0.10 threshold. This confirms the coherence of the experts' preferences. Furthermore, a sensitivity analysis using a simulation confirms that Road E remains the best option in 91% of all simulated scenarios, proving the model's robustness. Moving to our practical analysis, we bridge the gap between this paper and our course framework. Selecting a routing E via AHPGs provides a validated strategic baseline that internalizes environmental externalities, such as impacts on natural parks or urban areas, without the political complexities of forced monetary evaluation. Unlike standard metrics like CO2 per ton kilometer, which might misleadingly suggest that all routes are equal in distance, our AHP model captures qualitative categorical trees like ecological fragmentation. However, the paper solution is only a starting layer. To avoid the real-world inefficiencies, we must complement this strategic choice with dynamic monitoring of noise and emission and operational synergies such as eco-driving. Furthermore, adopting a regional collaboration approach, as suggested by facility relocation models, would allow companies like Hydrenasa and Gamesa Eolica to share a consolidation hub near Pamplona, structurally increasing vehicle load factors. Looking at the operational side, we must maintain an end-to-end focus because Pyrenean savings are easily nullified if last-mile urban distribution remains unoptimized. To truly mature this model, we should transition from static route assignment to active green VRP and VRP with backhauls. Backhauling, in particular, represents a massive opportunity to eliminate empty return runs, which are one of the primary sources of waste in international transport. We must acknowledge the structural limitation of the paper. The current AEHP is static and does not account for dynamic variables like road gradients or traffic. Therefore, it should be used as a dynamic tool subject to periodic recalibration as EU environmental targets evolve. Ultimately, this study offers the strategic layer of a two-level decision architecture, which we must complete with the operational and mathematical flow models covered in this course. In conclusion, the study by Faulin et al. Showed that integrating strategic planning with daily operations is the only way to translate theoretical savings into lasting benefits. True green logistics requires a cohesive focus across the entire supply chain. Thank you very much for your attention.